Writing the equation of a polynomial function when provided with the zeros of that function is a relatively straightforward process. However, there are a lot of minor details in the work, things that go back to lessons from earlier modules, that have the potential to derail that work. So we want to be careful as we do our work here, despite the fact that the easy identification at the beginning makes you feel like you're already done. So looking at this polynomial here, we have three intercepts. We've got an intercept right here, an intercept right here, and an intercept right here. And when we do this work, we're looking specifically at the x-intercept. We'll get to the y-intercept, but right now we're looking at the x-intercepts. So we do have three of them, and each one of those y-intercepts is going to be turned into a factor for the polynomial. So in order for -1 to be an intercept, x plus 1 must be a factor. In order for 2 to be an intercept, x minus 2 must be a factor. And in order for 6 to be an intercept, x minus 6 must be a factor. Understanding those three factors as a representation of the three intercepts, it would almost feel like we were finished. However, we should clock from the very beginning that if this is a cubic polynomial, I have three x's. I have an x, an x, and an x. If this is an odd-powered polynomial, an odd-degree polynomial, I should notice that my end behavior is actually backwards right now. So at the very least, without doing anything else, I probably want to put a negative in front of all of this. And we'll deal with that negative at the end after we multiply out to create the standard form. But that reversed end behavior of what we anticipate from an odd-degree polynomial indicates that we're going to be going the other direction. So multiplying out this polynomial, we're going to leave the negative sign for right now. Multiplying the first two factors gives us x squared minus x minus 2, and we're still times x minus 6. Now we have a trinomial times a binomial, which means we're going to create 6 terms through that multiplication. We're going to leave the negative out here. X cubed minus 6x squared minus x squared plus 6x minus 2x and then plus 12. And you can check me on each one of those multiplications. I took each term from the first trinomial and multiplied it by the two terms from the binomial. Combining what we can combine and simplifying what we can simplify, we have x cubed minus 7x squared plus 4x plus 12. Running through that negative sign now, because we would be at the end of creating a polynomial, negative x cubed plus 7x squared minus 4x minus 12. Normally, you would think you were done. We've identified now a y-intercept of negative 12, but unfortunately, that does not match the y-intercept that I have from the graph. In order to get the y-intercept of my function to match the y-intercept of my graph, I'm going to need to multiply my function by 4. So all of the terms in my function are going to get multiplied by 4 in order to get those y-intercepts to match. And we have a new function, negative 4x cubed plus 28x squared minus 16x minus 48 is equal to y. And before you think to yourself that that's going to change a lot of the work, it really doesn't. If we imagine going back to the factored form, and I imagine putting a 4 out here, which is essentially what I did. I multiplied all of the all of the polynomial by 4. If I go back to the factored form and place a 4 out there, that's not going to change the fact that this will still be 0 when x is -1, and this will still be 0 when x is 2, and this will still be 0 when x is 6. I'm allowed to scale up the multiplication to get that y-intercept to match, thanks to this factored form and thanks to what we already know about polynomials and how they interact with the y-axis.